I'm Rebecca Davies, a postdoc at Swinburne, and I'm going to tell you today about some of the results from the XQR30 survey. So first of all, I want to thank the previous speakers in this session for giving us a really good overview of outflows and the CGM and why we care about these for our understanding of galaxy evolution. In this talk, I'm really going to step away from these studies in the local universe and take us all the way towards the epoch of reionization and how we can use metal absorbers to study outflows and enrichment at that epoch. So we've already seen that galaxies in our present day universe are embedded in these rich multi-phase halos of gas that we call the circumgalactic medium, or the CGM. Now, a key aspect of the CGM is that the metals that we find there were not formed in situ. They were formed in galaxies through stellar and supernova nucleosynthesis, and then transported into the halo through galactic winds. This means that if we go to high enough redshift, we should eventually find galaxies with completely pristine halos. And so with this kind of motivation in mind, the aim of this study is to study how the properties of the CGM have evolved from a redshift of around 6 to 4.5, and then use this information to try to understand the early buildup of metals in the CGM and place some constraints on the formation redshifts of the first galaxies. So unlike the galaxies that we've just seen, the CGM at high redshift is generally much too faint to study in emission, so we have to go to other tools. In particular, we can use metal absorption lines to probe the chemical content and ionization state of the gas. So photons from bright distant quasars will travel through galaxy halos on their way to the Earth, and each of these halos imprints a series of absorption lines where the relative strength of the absorption lines indicate information about the abundance ratios and the ionization state of the gas. And so essentially, if we can get a sample of bright quasars at the epoch of reionization, we can start to study how the properties of galaxy halos have evolved over cosmic time. A key tracer of enriched gas in galaxy halos is carbon-4. This has an ionization potential of 47.9 electron volts, which means that it traces low-density gas deposited into the halo by outflows. Previous studies of carbon-4 absorption at high redshift have found preliminary evidence that it becomes much less prevalent above a redshift of 5 or so. This could indicate that the period between redshift 6 and redshift 5 is a really key epoch for the buildup of metals in the CGM. However, C4 only probes a single ionization state of carbon. So we also have to consider the possibility that what we're seeing is a change in the ionization state of the gas. This cartoon here illustrates one possible scenario where the total carbon abundance of the CGM remains constant over this redshift range, and the decrease in carbon-4 is balanced by an increase in the amount of carbon in other ionization states. Now, unfortunately, these previous measurements were not accurate enough to be able to distinguish between these scenarios. So we need more statistical information. This is where the XQR30 survey comes in. So XQR30 is an ESO large program that obtained extruder spectra for 30 quasars at redshifts 5.8 to 6.6. In this graphic here, you can see about half of the spectra, and the key features here are that the spectra are very high signal to noise for redshift 6 quasars, and you can see tons of these little dips in the spectra. All of these are metal absorption lines that we can use to study how the properties of the CGM have evolved over time. Now, prior to this survey, there were only 12 spectra of similar quality in the archive. So here we've quadrupled the sample size that we can use for detailed studies of absorber properties. So once we have these spectra, the next thing that we want to do is identify the absorption lines and measure their properties. We used a combination of automated line finding and visual inspection and cataloged around 800 absorption systems in these spectra, spanning redshift 2 to 6.5. The wide redshift range is a really unique aspect of this sample because it allows us to self-consistently compare the properties of absorbers all the way from the era of galaxy assembly to the peak epoch of star formation, which is a really significant chunk of the early history of the universe. In this video here, this gives you a bit of an idea for the scale of the data set. So in this first frame, I've just showed the metal absorbers that we detect in a single spectrum. And in each frame of the video, I'm going to add in absorbers from an additional spectrum. So you can see how having a lot of spectra really makes a difference. And each row in the panel shows absorbers detected in a different ion. And we plotted weaker absorbers in lighter colors over the top so that you're able to see them over stronger absorbers. And basically, we have a really unprecedented large sample size in this survey that we can use for statistical studies. Now, this is intended as a legacy catalog, and it's currently in team review stage with public release planned for late 2022. So with this catalog, we have a much larger sample of C4 absorbers than any previous compendium in the literature. So the previous largest study was based on 12 quasars, whereas we have 42. So this is a factor of 3.5 increase in sample size and really allows us to make much more accurate measurements of C4 absorber properties. So in this project, the primary quantity that we are interested in is the C4 cosmic mass density, or omega C4. You can think of this as a similar quantity to the cosmic star formation rate density. It's defined as the mass in carbon-4 per unit co-moving volume as a fraction of the critical density of the universe at redshift 0. In this plot here, you can see our measurements in black compared to previous studies in the literature in the colored markers. Our results are in good agreement with previous studies, but we were able to make more precise measurements and in more redshift bins, and this really helps us when it comes to the interpretation. We find that omega C4 increases quite quickly over the redshift interval between 5.8 and 4.7, and it grows by a factor of 5 over a period of only 300 million years. So this is quite a rapid change. So now we can start to think about what is actually causing this evolution. As I mentioned earlier, one of the possibilities is that we're seeing basically an increase in the amount of carbon in the CGM due to gradual enrichment by outflows. The cosmic mean metallicity at a given redshift is expected to scale approximately with the integral of the cosmic star formation rate density. And if you take, say, the McDowell and Dickinson model, this would increase by a factor of 2.2 over the redshift range we probe. This is less than half of the observed evolution. However, this simple model doesn't take into account the fact that the metallicity of the CGM could lag behind the metallicity of the ISM, because outflows actually take a finite amount of time to travel from galaxies to the halo. If you take this into account in your model, you would find that to explain the entire evolution, you need a delay time of around at least 500 megayears. This is not out of the question from the perspective of the galaxy formation redshifts, so it would imply a formation redshift around 9 to 13. However, what is problematic is that if you convert that time into a distance, it would imply the absorbers are at a distance of 50 kiloparsecs or more, which is bigger than the virial radius of the galaxies at that redshift. So it seems that we might also need to invoke some kind of change in ionization to explain this evolution. Okay, thanks. Yeah. So we can also explore whether or not we might be seeing a change in the ionization state of the gas by exploring the balance between C2 and C4. So we might expect to see a change in the ionization state because neutral hydrogen in the intergalactic medium can absorb some of the high energy photons and soften the UV background. So maybe following the end of reionization, you could see some hardening of the UV background. And there is some kind of evidence for this in previous studies. So this is the ratio of C2 to C4, and it is increasing with redshift, indicating that more metals are in a lower ionization state environment at a higher redshift. With the XQR30 data, we find that variations in the C2 to C4 ratio could potentially account for about up to half of the observed evolution. So basically the overall conclusion here is that we need both a combination of chemical enrichment by outflows and an increase in the average ionization state of carbon to explain the observed evolution. And I'll just leave my summary up. Thank you.
Thank you.